Prepare to witness a groundbreaking discovery that will revolutionize our understanding of the universe. Join us as we explore the incredible phenomenon of gravitational waves, a concept first predicted by Albert Einstein over a century ago. In this video, we'll take you on a journey through space and time, revealing the mind-bending reality of these waves and the revolutionary technology that made their detection possible. Get ready to have your mind blown and your curiosity piqued as we delve into the fascinating world of gravitational waves. Watch this incredible video and witness the confirmation of Einstein's prediction. What are gravitational waves? Gravitational waves are ripples in space-time caused by some of the most violent and energetic processes in the universe. Albert Einstein predicted the existence of gravitational waves in 1916 in his general theory of relativity. Einstein's mathematics showed that massive accelerating objects, such as neutron stars or black holes orbiting each other, would disrupt spacetime in such a way that waves of undulating spacetime would propagate in all directions away from the source. These cosmic ripples would travel at the speed of light, carrying with them information about their origins, as well as clues to the nature of gravity itself. The strongest gravitational waves are produced by cataclysmic events, such as colliding black holes, supernovae, massive stars exploding at the end of their lifetimes, and colliding neutron stars. Other waves are predicted to be caused by the rotation of neutron stars that are not perfect spheres, and possibly even the remnants of gravitational radiation created by the Big Bang. Einstein's prediction. Though Einstein predicted the existence of gravitational waves in 1916, the first proof of their existence didn't arrive until 1974, 20 years after his death. In that year, two astronomers using the Arecibo Radio Observatory in Puerto Rico discovered a binary pulsar, exactly the type of system that general relativity predicted should radiate gravitational waves. Knowing that this discovery could be used to test Einstein's audacious prediction, astronomers began measuring how the star's orbits changed over time. After 8 years of observations, they determined that the stars were getting closer to each other at precisely the rate predicted by general relativity if they were emitting gravitational waves. Since then, many astronomers have studied pulsar radio emissions. Pulsars are neutron stars that emit beams of radio waves, and found similar effects, further confirming the existence of gravitational waves. But these confirmations had always come indirectly or mathematically, and not through direct contact. Gravitational waves, first encounter. Gravitational waves carry information about their dramatic origins and about the nature of gravity that cannot otherwise be obtained. Physicists have concluded that the detected gravitational waves were produced during the final fraction of a second of the merger of two black holes to produce a single, more massive spinning black hole. This collision of two black holes had been predicted but never observed. The gravitational waves were detected on September 14, 2015 at 5:51 a.m. Eastern Daylight Time, 9:51 UTC. by both of the Twin Laser Interferometer Gravitational Wave Observatory, LIGO detectors, located in Livingston, Louisiana and Hanford, Washington, USA. The LIGO observatories are funded by the National Science Foundation, NSF, and were conceived, built, and are operated by Caltech and MIT. The discovery, accepted for publication in the journal Physical Review Letters, was made by the LIGO Scientific Collaboration, which includes the GEO Collaboration and the Australian Consortium for Interferometric Gravitational Astronomy, and the Virgo Collaboration using data from the two LIGO detectors. Based on the observed signals, LIGO scientists estimate that the black holes for this event were about 29 and 36 times the mass of the Sun, and the event took place 1.3 billion years ago. About 3 times the mass of the Sun was converted into gravitational waves in a fraction of a second, with a peak power output about 50 times that of the whole visible universe. By looking at the time of arrival of the signals, the detector in Livingston recorded the event 7 milliseconds before the detector in Hanford, scientists can say that the source was located in the southern hemisphere. The existence of gravitational waves was first demonstrated in the 1970s and 80s by Joseph Taylor, Jr., and colleagues. Taylor and Russell Hulse discovered in 1974 a binary system composed of a pulsar in orbit around a neutron star. Taylor and Joel M. Weisberg in 1982 found that the orbit of the pulsar was slowly shrinking over time because of the release of energy in the form of gravitational waves. For discovering the pulsar and showing that it would make possible this particular gravitational wave measurement, Hulse and Taylor were awarded the Nobel Prize in Physics in 1993. Why are these waves so hard to detect? By the time gravitational waves reach us from the distant events that spawn them, they distort spacetime by an utterly minuscule amount. The distortion is many times smaller than the width of a proton, one of the particles in an atom's nucleus. Measuring such minute changes in length is pretty much impossible for most instruments. So how does LIGO work? The LIGO facility consists of two identical L-shaped detectors in Washington State and Louisiana, each of which employs lasers and mirrors to measure the tiny changes in spacetime made by passing gravitational radiation. The name of the game in each location is to record the change in distance between mirrors parked at each end of two perpendiculars, 2.5-mile-long arms. Observation paved the way. The observation also paves the way for testing general relativity as never before, Kamienkoski says. Until now, physicists have studied gravity only in conditions where the force is relatively weak. By studying gravitational waves, they can now explore extreme conditions in which the energy in an object's gravitational field accounts for most or all of its mass, the realm of strong gravity so far explored by theorists alone. With the black hole merger, general relativity has passed the first such test, says Rainer Weiss, a physicist at the Massachusetts Institute of Technology, MIT, in Cambridge, who came up with the original idea for LIGO. The things you calculate from Einstein's theory look exactly like the signal, he says. To me, that's a miracle. The detection of gravitational waves marks the culmination of a decades-long quest that began in 1972, when Weiss wrote a paper outlining the basic design of LIGO. In 1979, the National Science Foundation funded research and development work at both MIT and Caltech, and LIGO construction began in 1994. The $272 million instruments started taking data in 2001, although it was not until the upgrade that physicists expected a signal. In conclusion, the confirmation of Einstein's theory of gravity waves is a monumental achievement that marks a significant milestone in our understanding of the universe. The detection of these ripples in spacetime has opened up a new window into the mysteries of our universe, allowing us to observe cosmic events and phenomena that were previously invisible. With ongoing research and new technology, we can only hope to continue pushing the boundaries of our knowledge and unlocking the secrets of the cosmos. Don't forget to subscribe to our channel, or you will miss